If the Earth is flat, some issues need to be addressed. Engineering the flat Earth, is there any hope? What is the shape of the Earth? If round, we are done. Gravity and Newton's laws explain everything. If flat, there is much to be worked out. Let's have a look. What does a flat Earth theory require? Apparently it needs a dome to contain the atmosphere. It needs some means to hold everything down because gravity isn't a thing. It needs a means to allow the sun and moon to travel in a way that is identical to observations. It must explain and predict eclipses, both solar and lunar. It must explain and predict the motion of the planets, including retrograde motion. In short, it must explain every phenomenon that we experience in everyday life. First we need the size of the flat Earth. The diameter of the flat Earth must equal the circumference of the globe, otherwise everything won't fit. Simple algebra shows that the area of the flat Earth is 2.5 times larger than the globe Earth. You would think someone would have noticed this by now. Let's start with the dome. The flat Earth's diameter must be the same as the globe Earth's circumference. Let's call it 25,000 miles. For simplicity, let's assume the dome is a half sphere, the same diameter as the flat Earth. So the dome height must be half the Earth's diameter or 12,500 miles. We won't worry about the sun, the moon, the stars, the planets and all the other objects that we see in the night sky for this discussion. We will just focus on the mechanical aspects of the dome and what it must do. It must contain the atmosphere at pressure P0. It must attach to the flat Earth in some way so the atmosphere doesn't leak out. It must support its own weight. It must be invisible, because no one has ever seen it. We can calculate the force on the dome due to an arbitrary pressure. Force equals pressure times area, so the pressure acting on the annulus dA gives a force dF. We only care about the vertical force trying to lift the dome off the flat Earth. After some substitution and integration, we find the lifting force is just the pressure times the area of the flat Earth. So what does this mean? The area of the flat Earth is equal to 490 million square miles. Atmospheric pressure at sea level is 14.7 pounds per square inch. So the force, F, trying to lift the dome off the flat Earth is 2.9 times 10 to the 19th pounds. Wow! That's a big number. How would the dome be attached to the flat Earth? Let's use bolts around the edge. If we divide the total force by the circumference, we can figure the force per foot. We would need over 500,000 1-inch bolts for every foot around the dome. But this is impossible. Let's think about this. The dome must have some weight to offset the pressure. The volume of the dome is equal to its area times its thickness. If we use plexiglass with a thickness of 1 inch, then the dome would weigh 1.5 times 10 to the 17th pounds. Wow again. That is 58 billion Nimitz-class aircraft carriers. But that's not even close to the upward pressure force. That is only about 1% of the upward force. The dome would have to be 16 feet thick for the weight to equal the pressure force. These are incredible numbers, but we are not done yet. We know the atmosphere has a gradient, so the force should be less because the atmospheric pressure decreases with altitude. This pressure gradient is easily measured, so it must be real. There is an exponential decrease in pressure as the altitude increases. Using this relationship, the pressure at 300,000 feet, almost 60 miles up, is negligible. When we add all the pressure forces up to the top of the dome, we get the total upward force of 9.3 times 10 to the 12 pounds. This is less than before but still a very large number. Now the dome weighs more than the pressure trying to pop it off. The problem is, the top 12,440 miles of the dome isn't necessary because there isn't any air up there. Wow! Maybe we don't need a dome after all. This graphic shows the calculation of the force on the dome for a gradient pressure atmosphere. The force is due to the pressure, which decreases with altitude, on the dome wall, which is constantly getting less steep, therefore showing more area in the upward direction. The total force is the sum of the vertical forces on each annular section of the dome. Now we have a dilemma. If we have a constant pressure throughout the dome can't be held down onto the flat Earth. There aren't bolts strong enough to handle the job. If we have a gradient pressure in the atmosphere, only the bottom 0.8% of the dome has any air in it, the rest is empty. Then we don't need a dome at all. Just like the globe Earth. What if the dome were very thin, like a balloon? Let's assume a 20-inch diameter balloon with a 5,000-inch thick shell. The thickness to diameter ratio is then 1/4000th. Now multiply that by the dome diameter of 25,000 miles, and get a shell thickness of 6.25 miles. Wow! That is much thicker than our previous guess. A balloon-like shell would still be fragile. It could pop. What is the weight of a dome like that? 5.9 times 10 to the 22 pounds. That is a huge weight. The shell would require a volume of plexiglass almost equal to half the moon's volume. Double wow! Impossible. Putting the weight of a balloon-like dome in perspective. A Nimitz-class aircraft carrier weighs 2.6 million pounds. It would take 23 followed by 15 zeros of them to equal the weight of a balloon-like dome. Lined up end to end, they would reach the North Star Polaris not once, but there and back again over 2 times. Maybe a shallow dome makes more sense. The force calculations are similar but the results are dramatically different. For the gradient pressure, the upward force is increased to 1.4 times 10 to the 17th pounds. This is 150,000 times greater than the half-sphere dome gradient force. Luckily this balloon-style dome weighs 50,000 times more than this so the weight will hold it down. However, this weight is 2,000 times more than the dome material can stand. It would just collapse by being crushed under its own weight. So the shallow dome weighs less. But, using the thin shell balloon analogy, this shallow dome would still weigh 10 to the 20th pounds. That's enough aircraft carriers to get half the way to Alpha Centauri. And with the low angle at the edges, you could see the dome. Yet the atmosphere would still only fill the bottom 1/16th of the dome. So why do we need the dome? The dome makes no sense. Where does that leave the flat Earth dome? The proposed flat Earth is unimaginably large. A dome large enough to cover it would simply collapse under its own weight. While seemingly very thick, the dome would be as fragile as a balloon. The dome is mostly empty, just like space, a vacuum. While the dome looks nice drawn over the flat Earth, it just isn't necessary. It's impossible. So the dome is our first flat Earth project and a failure. Some follow-up questions. How thick is the flat Earth? What is it sitting on? How do the planets move in the dome? How do the sun and moon move in the dome? Since density and buoyancy are not forces, what keeps everything down? If the sun is just a light, where does the energy we feel come from? If the moon emits cold light, what does that mean? What kind of photon is that? Why hasn't it been noticed that the distance around the South Pole is 150,000 miles while it is only 10,000 miles around the Arctic Circle? Why hasn't it been noticed that flying from east to west requires a constant right turn? Why is there complete disregard for the distances and times for flights in the southern hemisphere? How did Amundsen get to the South Pole if there are people waiting there ready to shoot or arrest anyone who approaches the ice wall? These and many more questions are waiting for answers from flat Earth proponents. Don't hold your breath waiting for an answer.